Unfortunately, due to technical problems, my co-chair, Professor Yuei-An Liou, has not been able to check in yet. Let's hope that he can solve this during the session. I would want to take a brief minute to introduce myself and my co-chair. So my name is Tom Vanwalleghem. I'm from the University of Cordoba in Spain. My co-chair, Professor Yuei-An Liou, is from the Center for Space and Remote Sensing Research at the National Central University in Taiwan. So we have a lot of interesting speakers today for this session. So I really thank you all for attending, and especially to the speakers. When we had to select the oral talks, it was very difficult because there were a lot of good contributions. So I definitely want to recommend you to go to the poster booth. The contributions that we have, we try to cover everything that we try to define in this session. So covering advancements in technology, both social and physical sciences, exploring drought and climate change, and also including the visions of politics, institutions, and society as a whole. Like, for example, the last presentation is more directed towards that aspect of drought research. So I think it's a very complete image of everything that's going on in droughts. We all know that droughts are very common, very important. They cause a lot of economical loss and social damage and are expected to increase under climate change. So I hope this session helps in contributing to our knowledge on this topic. And without further ado, I will turn off my microphone and I will leave the floor to our first speaker, which according to the program is Erika Lucia Arias Ramirez from Colombia. So welcome.
Hi, everybody. I am Erika. So for the presentation, I am going to turn off my camera because I am in a remote rural area and my connection is a little bit weak. A sustainable irrigation district in Colombia. So, under responsible water consumption in agriculture, prior to construction, proper planning is needed. So here in this study, we consider the watershed as a figure to develop irrigation strategies by estimating monthly water yield assessed with SWOT. So the analysis was made in a predominant agricultural land named Monterrey, the place where I am now, and they are looking for an implementation of an irrigation district here in this area. Is a section of the Tua Basin. This section accounts 39% of the total producers in the municipality. So from the high variety of agricultural system that we find here, legal extractions are represented mostly by fish farms with 75%, and it is followed by domestic uses with 21%. So this region faces challenging aspects for this modeling. Like the high variability between rainy and dry seasons, we have a monomoral regime, the vulnerability to drought and ENSO events, data scarcity, and the most important, an engaged catchment. So to overcome the challenges, we choose a similar geomorphology basin that is named Caballaro, and it was selected to calibrate SWOT to understand the spatial and temporal hydrology in this study area, in this section of the Tua Basin, to derive strategies for an irrigation district feasibility in an area that corresponds mostly to 29 hectares. Talking about the methodology, we use several sources of information to calibrate SWOT model for Caballaro Basin. And this time window was from 1995 to 2015. This is 21-year period. Then from Caballaro, we modeled to a basin using the same sensible parameters. And here we obtain monthly water yields also for a scenario that is considered RCP 8.5 from 2016 to 2045. Here, we choose this unfavorable scenario because of the territorial planning in this region. Here, we have a regional tendency for developing agribusiness, majorly on private land. So it's difficult to promote different policies. The outcomes were used to estimate agricultural unmet demand by seasonality. And here we consider also the ecological flow. To the future scenarios, we generate clusters considering 20 GCMs at daily time series. But we cluster them using the R-up, like is shown in this figure. And then we match this monthly differentiation of the GCMs with the daily, and in order to match them and to obtain 4 clusters more. The climate change scenarios were confronted with current demand that correspond to 0.7 cubic meters per second, plus the ecological flow that corresponds to 25% of the lowest multi-year average flow in the streams registered for each modeling. As a result, we run Caballero successfully, defined by periods of model warm-up, calibration, and validation. So here, the best calibration that we could obtain presented a good Nash efficiency, a very good percent bias, and a satisfactory coefficient of determination. According with that, we said that this have a good capacity to simulate the hydrological dynamics in Caballero Basin. But for the validation made for 2014 to 2015, we noticed changes in the efficiency coefficients. This reflects a very poor model in periods of extreme events. If you notice here, the standardized precipitation evapotranspiration index in 2015 was registered El Niño phenomena in this area. So here, even though we have this problem, we took the decision to model the section of Tua Basin because of this good performance prevailing in most of the time period. The Tua Basin was modeled then with this with the previous model, and we obtained 37 sub-basins. The balance is given here in the slide, and the monthly water yield is averaged to generate the annual water yield, as we can see in the map. If you see here, we can find in the upper north side of the basin, 9 sub-basins that correspond to the greatest contributors to the Tua River. And in this part, we can see the lower contribution. As for the future scenarios, RCP 8.5, we notice there are climate variations impacts geographically and seasonality differentiated. Here we can see that there is a decrease in cluster 3. We registered 4% less occurrence here in the upper part. Whilst in the other scenarios, we show a slight positive and negative variation. Overall, we can see that everything indicates that we have a water rise for 5 scenarios in this western part of the basin. And accordingly, with this picture that we have here, or these maps, more water in the form of mean annual precipitation may be entering the basin in a cluster, an ensemble, that is this one, the E, in cluster 2 and cluster 4. And we have here less entering water recorded in cluster 1 and in cluster 3. And to sum up, we are comparing the demanded flow with the assessed supply scenarios, and we found that for 28 evaluated years, that with a low rate of flow of 20 cubic meters per second, it remains constant during dry months that there are from December to March. But when we assume a lower flow of 10 cubic meters per second, there is registered in cluster 4 14 years with low levels, and there is a similar pattern followed by cluster 1 and 3. Finally, we deduce that with this evident increase in water demand to the future, the problem tends to be driving towards implementing better water management strategies. And we also found in groundwork that farmers' petition of an irrigation district may be due to short ages experience over secondary tributaries placed in the lower western part of the basin. So also, we found that high water demand coincides with the higher production of fish farms, avocado, and palm oil taking place from January to April. So the recommendation is to collect water during the 8 months of rainy season in this region, either through individual private microcatchment as the one we are building nowadays in our demonstrative farm, or a regional reservoir. Thank you. And I also made a small poll in order you can participate and give me some of your thoughts. Thank you so much.
Thank you very much, Ms. Arias Ramirez. Are there any questions? I believe you can submit them through the application. I don't see any questions popping up for the moment. If not, I have a question myself. I found it a very interesting presentation with lots of different aspects taken into account. I have a rather small screen on my computer, so I did not capture all the results, but I think I was able to see the most important ones. Do you think that your results for water yield, difference in water yield, one of the last graphs you showed, do you think that accurately represents the ENSO events, or do you think these global climate models have problems representing these events? You mentioned at the beginning you had problems with validation in some years.
Yes, it happened that we had very data scarcity, and we have a final period of 2015. Then here we have a problem. In my region, we have a phenomenon of El Niño from 2014 to 2016. So precisely my model was validating is in this moment of the occurrence of the phenomena ENSO. So here we have a very problem, and it was very difficult to us to find a solution to it. The model here is presented as deficiencies. So we need more observing data, measure data to analyze better the correspondence of the model and what is really happening here. And Colombia have a very diverse gradient. So in the place where I am, that is the Orinoquia region, we have a monomodal regime. But in the other part of the country, we have a bimodal regime for precipitation. So we cannot conclude that easy what is happening in the model. So it requires further analysis.
Excellent. Well, I hope you can continue to work on this. Fantastic.
We are doing that. We are very happy of doing that.
Okay, so let me see. I'm not sure if our co-host, co-chair, Dr. Yuei-An has been able to log in yet. I don't see him. If not, I will continue to chair this session. So can the next speaker, which is Kenneth Gutierrez Garcia, can you please prepare your presentation, and you have the floor. I think we are right on schedule. I think it's about 15 minutes per presentation, so you can go right ahead whenever you are ready.
Thank you.
And if there are questions I see that we have a large audience, 34 participants for an online event, which is quite good for, everybody has a lot of conferences online, etc. So it's very good. Thank you. If you have questions, please submit them through the chat function or through the questions and answers.
So can you see the presentation?
Perfect, perfect.
Okay. Well, hello to everyone. My name is Kenneth Gutierrez Garcia. I'm a master's degree student in geography at the University of Costa Rica. And today I will talk about one part of my master thesis that is about probabilistic analysis of meteorological drought using Markov chains and Bayesian networks in the seasonally dry tropics of Costa Rica. As motivation, we have that in 2016, one of the most severe droughts of the last decade affected 3.5 million people and caused a loss of crops up to 90% in the Central American dry corridor. And the North Pacific region of Costa Rica forms part of this dry corridor, which is characterized by at least 4 months of dry conditions. These dry conditions are projected to increase in intensity and duration in the near future. So to adapt to this condition, we need to increase the drought forecasting ability to help decision making. The study area is the North Pacific region of Costa Rica, especially the Tempisque River catchment, that is this in red. In my thesis, I'm using three meteorological stations, that is these triangles in green. But in today's presentation, I will focus only in the airport station because we have the longest data set available for this region, that is almost 83 years, since 1937 to 2020. And this is the perfect example of this climate region in Costa Rica because it has a very marked dry season from December to April. That this one should not be confused with drought because there is also like a misconception here in Costa Rica that, I don't know, in January or February there is drought happening because there is less precipitation, but this is a natural phenomenon. And then there is also a very marked rainy season starting in May throughout November. So our objectives are to analyze the performance of probabilistic models, such as Markov chains and Bayesian networks, with meteorological drought events. So we apply first and second order Markov chains, then we evaluate Bayesian networks with 2- and 3-dimensional copulas, and then we compare their performance to determine which is the best suited to the study area. So as methods, we have the Markov chains. As we saw in this figure, in the monthly average precipitation, there is a very marked seasons. So we need to have different probabilities for each month. So that's why we use non-homogeneous Markov chains. So it means that the probability changes each month and according to what happened in the month before. This is their formula for this first order and the second order. The idea is that the probability of any state in any month is given by what happened in the month before. And the same idea is the second order, only that it includes 2 months before to know what will happen in the future or in the next month. The Bayesian networks, they are a set of conditional probability distributions. So to get these conditional probability distributions, we use copulas. Here also we have different copulas for each month. And even though, for example, June and July has the same copula type, they have different parameters. So they have different distributions according to each month. And the evaluation we use, or what we talk here, is the ranked probability score because it's simpler. This is only a difference between the model or the forecast and the observed data. So if there is no difference, it means that the forecast was the same as the observed data. So that will be a perfect forecast, and that should give us an RPS value equal to 0. So as data input, we have only precipitation because we want to forecast meteorological drought. So when we have this precipitation data, then we apply the standardized precipitation index of 1 month. And then we reclassify this index into 4 categories. The first one being no drought category or state 0. The second one is the moderate drought or state 1, severe drought or state 2. And the last one is extreme drought or state 3. As results, well, we had the meteorological drought events in the time series from 1937 to 2020. We can see that, well, here in yellow are the moderate droughts, the extreme droughts are in orange, and the severe drought are in orange, and extreme droughts are in red. And the blank tiles are the no drought category. So we can see that the meteorological drought events only had happened in the rainy season between May and November. There is no a clear visual pattern of how these drought events behave. So there is any month with more droughts or less droughts in the rainy season. But we can see that, for example, from the 60s to the 80s, there was a lot of activity in meteorological droughts. But then in the 90s, there were less activity, except for the 1997 and 1998, where there was a strong El Nino that affected the area. One important thing that I forgot to mention is that we divide this time series into 2 periods. The calibration period from 1937 to 1999, and from the other period is the validation period from 2000 to 2020. So this heat map also helped me to show how Markov chains work, to visualize how it works. For example, here we have May with extreme drought in 1951. So Markov chains, what search for is how many a transition happens between any given month. So for example, this May was in extreme drought, and the month before, April, was in state 0. So how many times this transition between 0 to 3 in these 2 months happens? So we can see that there is once, twice, and thrice in the calibration period. So this means, into probabilities, that there is a 5% probability that May will be in state 3 when April is in state 0. And the same thing with other states. As we see here, April has always been in state 0, so we don't have data available to any other chains from April to May, but we need to assign probabilities. So that's why we did this, assign 100% probability that if April will be in state 3, there is a probability of 100% that May will be in state 0, but we can be sure about it. And then in this other example, from the transition between August and September, there was this kind of issue with Markov chains that there was 2 times where August was in state 2 in the calibration period. One of those times, August transitioned to a September in state 0. And the other time that August was in state 2, it transitioned to a September in state 3. So it gives us a 50% probability that will be either 0 or state 3 in September. And this is an issue for decision making because we can be sure what shows. And then with Bayesian networks, as we have distributions, it always assigns a probability to each category. Continuing with the example of May, we have here in no drought state in blue, in yellow the moderate drought, severe drought in orange, and red have the extreme drought. And these vertical lines show us the observed meteorological events that happen in the validation period. So we can see that historically in the validation period, the no drought state has the most probability of happening. But when we observe a drought, this probability drops below 70%. And the same thing with in May 2015, there was a extreme drought, and it drops almost to 60%. And the probability of any type of drought or category of drought rises a little. For example, the extreme drought has been always being in below 5% probability, but in this case, in this May, it rises to 11% probability. So even though the model shows us that there is a major probability that there is no drought in this month, but when we analyze the historical behavior, we can see that when there is a drop and a raise in these probabilities, this could mean that there will be a drought. So it's like an early warning. And the same thing with September. Even though this is more constant, the probabilities that give us, there is also drops when we observe any drought event. So as a result of the validation of only drought states, we can see that the Bayesian network of fifth order has the best performance in the rainy season, because that's when the drought events happen. It has problems in May and June, but this is because in the validation period, these 2 months has the less drought events. But then in August and November has the best performance. And this is good because one of the problems that we could face in the future is the extended dry season. So this could mean that the dry season could start in November or October. So if we can forecast a drought in these 2 months, we could adapt to those conditions. So in conclusion, Markov models perform better in the dry season, while Bayesian networks perform better in the rainy season. In the validation with only drought states, Bayesian networks obtain the best performance, so we can say that Bayesian networks is the best suited for this area. And by using distribution fittings, they can adapt to changing conditions from month to month, and to area, different stations, different time series, and so on. So I want to thank the organization and the shares for the opportunity. Thank you.
Thank you, Mr. Gutierrez. There are a few minutes left for questions, if anybody has any. I don't see any questions myself in the chat, but I wanted to ask you, Kenneth, that's a lot of work you've done there on statistical distributions and fittings and all that. Do you plan to continue this work? And in particular, my question is, I think, do you plan to use maybe other SPI values like SPI 3 or SPI 6? Would you expect that these are easier to predict because they are less volatile than SPI 1, which you used, if I understood it correctly?
Yes. Yeah, that would be a good addition, because Bayesian networks, as I said, it adjusts to any type of data that we give to it. So I think that 3 months would be perfect. 6 months could be different because the seasonality of this area. So, but we could see any other type of droughts, for example, a hydrological drought or agricultural drought. This could be a plus for the area because there is a lot of cane in this area, so they need a lot of water. So they could be useful.
Yeah, that's a very good point. Yeah, I work in agricultural drought issues myself, and I think we usually use SPI 3. So if you think that could be a good idea for your region, I would definitely like to see some results on that. There is a question from Ashwin Ram. What policy implications do you propose to mitigate extreme drought in this, I expect in this particular situation that you present in Costa Rica?
Well, what's the question? Sorry. What policies?
What policy implications do you propose to mitigate extreme drought? I guess Ashwin means what policy measures or what policy measures do you propose to mitigate drought in your region in Costa Rica?
We need to see to keep observing the behavior, because as drought is so silent, we don't know how it behaves or that. So we need to keep monitoring how it behaves in this particular area. If there is another, for example, there is El Niño that could affect the area, but there could be other oscillations. So we need to keep research for this type of things that could happen, and how the society use the water and how it demands the water, so we can to adapt to these two informations, the physical information, let's say in that way, and the social information, because as it's so silent, we need to keep an eye on it.
Yeah, no, I agree. And with your tools, if you can predict, then you can give policymakers a great tool to be in front of the measures. Thank you. Okay, I think we have to go to the next talk, which will be my own according to the program. So I will share my presentation with you. There is also a question, Kenneth, please check the chat box. Somebody is interested in your results and he wants to contact with you. So okay, so good afternoon, everybody, or good morning or good night, depending on where you are. My name is Tom Vanwalleghem from the University of Cordoba. I would like to thank my co-authors, Maria Pilar Jimenez and Juan Vicente Giraldes. As I've gone into screen share mode, I don't have access to the chat box on my screen. So if you don't see my screen well, please somebody open your microphone and say something, okay? Otherwise, I will assume that everything is okay. So I will talk about agricultural drought, and I will talk about two new indicators that we will use to assess agricultural drought, and then how we use those indicators to evaluate climate change effects in Spain. So I guess the background of this research is that we all know that drought is a major natural hazard affecting crop production and especially food security. I mean, it affects crop production, it affects crop prices, it affects various aspects of food security. It can also affect susceptibility to pests, etc. Now, there have been different studies already, and many studies have pinpointed that Southern Europe is a hotspot for droughts. And the country where I'm based and working, Spain especially, has been heavily hit by drought in recent years. You can see here some images of poor crop yields, and to the right, you can see images of an empty almost empty water reservoir, which then will heavily affect the crop production in the following years, because water in those reservoirs is basic for farmers for irrigating many different crops. Now, the problem even can be expected to worsen, because the importance of drought under climate change has been projected to increase by several studies already. Now, how we study drought and what we mean depends a bit on your definition of drought. I think most of you, if you work in drought, you will know this. There is meteorological drought, like the previous presenter has talked about, the scarcity of rainfall. Then there's a next step in droughts, severity, maybe we could say, which is when the scarcity in rainfall also affects our stream flow or water resources. Then there's the next step, which is agricultural drought, when the moisture which is in the soil water is not sufficient to maintain a crop, and the plants have stress. And eventually, if it is long enough, like here in the photo on the right, you can have mortality of crops or even of trees in natural areas. And then socio-economic drought, when this also affects the normal functioning of society. And we already have used different drought indicators. We know this, that SPI, the standardized precipitation index, is used a lot. The palmal drought index is used a lot. Then recently, the standardized precipitation index has been amplified to include evapotranspiration in the SPEI index. So there are a lot of indicators already out there. So why would we need something else? Well, there are different reasons. We know that plants, in addition to the severity of drought, we know that they are also subject to the duration and the frequency of drought. And in addition to this, it's quite complex. It gets a bit complex when you want to represent all those aspects at the same time and understand it, and you have to look at graphs and maps of severity, duration, and frequency, and sometimes they don't always say the same thing. This is to the right on the bottom a map of Europe from a recent publication by the colleagues by the group of Spenoni. And in the top panel, he represents drought frequency. In the middle panel, extreme drought frequency, a number of events per 10-year period. And then on the bottom, the drought severity, all for the same period, but you can see that different things are happening in different regions. So you have to have a wide vision to take it all in. So we are going to analyze the effect of climate change on agricultural drought, and we're going to use two novel indicators: static and dynamic drought stress, which I will explain to you in a minute, and we will do this for the period 2006 to 2100 using statistically downscaled climate change predictions. So basically, the idea of the static and dynamic stress indicators is the following. If you focus on the top panel, this looks very complicated, but it's just very simple. It's the evolution over time of the soil moisture. Okay, so the red level indicates a critical soil moisture level, which will depend on the plant type. Generally, different plants will experience stress at different levels. So as soon as the soil moisture drops below this level, you have a drought. And then here in this period, it goes above, so you don't have a drought anymore, and then it goes below and you have drought again. The idea is that we take into account the gray areas. This is expressed in the static stress indicator. This expresses the severity of the excursion below the soil moisture level. That's the static stress. And then we also take into account the duration, the mean duration of the stress event, and the number of stress events that we have over the year. The duration is TW, and the number of stress events is NW. Oh, sorry. Okay, I'm back. So dynamic stress takes into account not only the severity, but also here in the formula, you can see the number of stress events and the duration of the stress events. And now the interesting thing is that both indicators are only calculated during the growing season. These were actually proposed by the group of Porporato already in 2001 in ecohydrological research, but we haven't seen any applications in recent droughts research. So we thought it was very interesting to present these indicators and evaluate their potential here. So what did we do? We took climate change protections under the RCP 8.5 scenario. So we all know this scenario is one of the most severe ones, but we think it's useful to evaluate the worst case scenario in this situation. We did a statistical downscaling for 274 sites, which you can see here, the red dots distributed all over Spain. And so we had daily temperature and precipitation for the period 2006-2100 for these 274 sites. Then we ran a water balance, calculating basically from the precipitation and the temperature, evapotranspiration, runoff, percolation, and especially soil moisture change, which is what we need to calculate static and dynamic stress. So then we have a first look at some results, point per point, to see how good our model was doing. So it made sense. We took a dot here from the south of Spain. We see a decrease from 2000 to 2100 from the mean precipitation from 530 millimeters to 399 millimeters. This is the static stress indicator, and this is the dynamic stress indicator. So we see an increase in mean values from 0.49 in the first period to 0.57 towards the end of the study period. And you can see that the number of drought events, these are characterized by high values close to 1 or values of 1, which would be the maximum of this indicator. It always varies between 0 and 1. 0 would be no drought, and 1 would be a maximum drought. The number of high events of 1 also increases, especially if you look here at the bottom left panel to dynamic stress. We see that the mean value increases from 0.35 at the beginning of the century to 0.69, so it almost doubles towards the end of the century. And especially the number of extreme droughts increases from 2 droughts in the first period, in the first 30 years, 2 extreme droughts with a value of 1 in this first period, to 18 droughts in the last period here. And for a site in the north of Spain, this one here, it's in a much more humid climate zone. The precipitation drops from 997 millimeters to 831 millimeters here. There is really, if we look at the static stress and the dynamic stress, there is never an extreme drought as we had in the south of Spain, which is good, which as we expected. And the mean value increases from 0.07 to 0.18. So it increases, but it's not really problematic at this stage. And the dynamic stress increases more even, from 0.03 to 0.12. But again, it's never as problematic in the south of Spain. Then if we analyze the differences spatially, we can see that nowadays, for the first period that we analyzed, 2006-2040, we have already a very high drought stress. So these points are classified here in 5 classes actually. No stress would be white, and then from low yellow points to red, very high stress levels. So we already have very high stress levels here in the southeast of Spain nowadays, and then we can see that in the north of Spain we don't have almost any stress. This is maintained here towards the end of the century, and also we can see that the red dots actually spread out over the entire country. In the intermediate period, 2041-2070, this is not so extreme, but towards the end of the study period, we can see that almost the whole country, except for the more humid north, is covered by the dark red dots. This map is for the dynamic stress indicator. Here we can see a lot of white dots in the north of Spain. This means no stress there, stress 0. And then again, these are areas, this area here, and there's the Ebro Valley here in this area, which is already very stressed today. So in this area, we won't see a big change because they're already very dry today and very problematic today. But we can see a very big change in the rest of the country. Here, the rest of the country is in low to moderate stress, yellow to orange, and this all goes to red to dark reds, as you can see. If we summarize the same map and we express this as change, then in the top two figures we have static drought stress, in the bottom figure we have the dynamic drought stress, and now the different sorry, I lost my presentation again. The different colors here express the percent change. So we can see that blue to yellow colors, which is here in the periods in the areas that are already very dry. Here we don't see almost any change, not for the periods 2041 to 2070 compared to the first period 2006-2040, and also not for the second period 2071 to 2100 compared to 2006-2040. But for the rest of the country, we can see very important changes. The only thing here is that the most northern point don't appear in this map because they have no change. They were at zero stress and they ended up at zero stress. So we have no change there. And then if we do a kind of overall analysis to see now for all the points in the whole Spain, what does this mean? How can we relate static stress and dynamic stress to annual precipitation? Then for both, we see a very similar pattern. We see that there is kind of an area between 500, 600 millimeters of precipitation. If we go above that, we usually have very low dynamic stress values, but of course we can have a little bit stress depending on how the precipitation is distributed. If we go below that, then we can really have a lot of stress, or sometimes also no stress, but a lot of variability, depending again on how the rainfall is distributed across the year. And then there's how is dynamic stress and static stress related to each other? Because if there is a good relation, it would be interesting to calculate dynamic stress based on static stress. And we see that there is a good relation between both. Now, in terms of conclusions, what have we learned in this study? We found it very useful. We think we confirmed the potential of these static and dynamic drought indices, because especially the dynamic one integrates severity of drought, frequency of drought, and duration of drought in one sole indicator. We have seen that precipitation alone in this case, as we work with agricultural drought, is not such a good indicator. And especially we will see more frequent maximum droughts of values equal to 1, especially towards the end of the century. And then spatially, we see that areas that are already dry don't see a lot of changes. And in the rest of Spain, we expect a lot of increase in droughts. So thank you very much. If you have questions, I'll be happy to take them on. Oh, wonderful. I see that my co-chair, Yuei-An Liou, has been able to join us. Wonderful. Welcome. I see a question by Ajan Singh. How can you define meteorological drought in your study region? How much rainfall reduction is considered drought? I'm not sure if this refers to the previous presentation by Kenneth or my own. I think if I have to answer for my study area, I did not work with meteorological drought. We worked with agricultural drought. So that one, okay, thank you, my presentation. In our case, this would be when plants become stressed and you have an effect. Agricultural drought is when you have an effect on crop yield. So we are working to expand our study and compare our data with data on yields. If you ask about meteorological drought, I think most people use indicators like SPI, like Kenneth has showed, and then this represents a difference from a deviation from the mean precipitation during a certain period. So you have to assume a certain distribution of your data, usually gamma distribution, and then if there is a deviation of more than 1.5, like I think Kenneth showed, then you have a severe meteorological drought. Okay, Liou. Okay, you can hear me. I'm not sure. Your microphone is switched off, so I'm not sure if you. I haven't been able to hear you yet. No sound, unfortunately. Well, we will continue with the last presentation, which is by our colleague from Oxford, Kaur Harnoor.
Yeah.
And I will give you the floor.
Thank you.
Tom, can you hear me now? No.
Yes, we can hear you. Wonderful.
Oh, really? Okay.
Welcome.
Okay, good. Thank you. Let's continue.
Can everyone see the screen?
Yes, we can see it perfectly.
Okay, great. Good morning, everyone. My name is Harnoor, and I'm here to talk about the role of narratives in defining drought management. I'm a recent graduate of the University of Oxford, and this research was my master's thesis, so I am very excited to share my findings. And I want to thank the conference and the chair for giving me the opportunity to present today. To begin with, I think I'll just talk about what we understand of drought. So drought, of course, is a major climatic hazard, and it causes food and water insecurity along with ecological damage. And since in a lot of instances, droughts are exacerbated by anthropogenic activities, I thought it was important to understand the societal context. And I thought that in order to do that, an analysis such as a discourse analysis was central to understanding both the management of the drought and the subsequent responses to it. So in this study, I opted for a case study design, and I chose Maharashtra, which is a state in India, as my study area. And the reason for that is that Maharashtra has observed an increase in the extent and severity of droughts in the past couple of years, which I think, of course, poses serious water management challenges for the authorities there. And some of the socio-economic effects of droughts have been a spike in migration, localized water conflicts, malnutrition, and farmer suicides. Apparently, Maharashtra has observed the highest rate of farmer suicides in the country, with accounting at least 4,000 suicides out of 10,000 suicides that were recorded in India in 2019. So I thought it was essential to understand how media discourses define the institution declaration and response to droughts, because of course it's a very complex operation, and there are several actors, social actors, who are influenced by divergent agendas that come up with different solutions to droughts. So I thought it was essential to understand which social actors define what kind of solution that should be put forward to challenge, to come up with drought mitigation. So as I move to research gap and justification, I will just define what I understand of discourse and how I use discourse in this particular research. For me, discourse is an assemble of ideas, concepts, and categories through which we give meaning to a social and physical phenomena. In this instance, I do consider drought as a socio-physical phenomena, and it is important to realize that at any given point in time, there are several discourses and narratives which are competing for dominance and power. For instance, the narratives of a farmer would be very different from the narratives of a politician, because a politician has to look for to make sure that they have control and power of the government, whereas farmers have to make sure that they have access to water and other facilities. They have to make sure that they can eat. So there are different ideas to what they think a drought is and how we should tackle drought. So the aim of this research has been to investigate what is drought, who defines it, and what drought for whom. Whether when a drought is come about, is that drought particularly for people who are poor, or is it also for those who are rich and cannot handle the challenges that are brought out by droughts, and whose inconveniences have been neglected by it, and whose interests have been promoted with these narratives. So as I move forward, move to the next slide, I will be explaining, I will be elaborating on my research questions and methodology. There were two main research questions that focused, elaborated on this research. One was how Times of India, which is a newspaper in India, discursively represented droughts in their reporting. And the second one was what the effects of deploying specific narratives on the solutions proposed. I used a constructivist approach because in this research particularly, knowledge is not objective, but rather it is very objective, because our knowledge of droughts is something that is socially constructed. The knowledge of a farmer, again, would be very different from the knowledge of a government official or the knowledge of a researcher, because they have very different ideas of what a drought entails. And in this particular area in this particular research, I used a case study design, and I incorporated qualitative research by codifying the newspapers. The data source was an archival base of a popular newspaper, Times of India, some policy documents, and relevant literature. The reason I chose Times of India was because upon an analysis, it was found that Times of India was one of the most popular newspapers in the state. And I thought that it would best describe what the narratives that surround the state. In order to codify the newspapers and identify which newspapers were relevant, I used 3 keywords. One was droughts, another water scarcity, and third farmers. Water scarcity was used because a lot of the times in newspapers and in general discourse in India, people refer to droughts as water scarcity. So I thought it was essential to incorporate that aspect of the research as well. There were 2 inclusion criteria for this research. One was the genre and the other one was relevance. The genre, of course, was to make sure that the article was either a news, a report chronicle, or an opinion piece. And the relevance was to make sure that it was directly related to droughts and not other aspects of water crisis. For instance, a lot of articles that were removed from the data were those that were focusing on issues related to wastewater treatment plants or water access in urban areas. And then upon identification of 1,609 articles, I realized that articles were becoming redundant, and I had exhausted all measures. So I decided to stop at that. And then I later on coded these different articles based on different themes. For instance, I was looking at how locations describe our discourse around droughts, how social actors contribute to this discourse, and how different agencies and documents have different ideas of what a drought is and what we should do for that. Before I move on to my findings, I would just want to elaborate that there were 3 fields of literature that have contributed to the analysis of these findings. One is discourse theory, second is politics of scale, and third is post-structuralist political ecology. Discourse theory has a lot to offer. For instance, it lets you examine the nexus of power, information, and practice, whereas politics of scale lets you understand that scale is a social construct, and of course it's relational, fluid, and fixed, and that when we say that this is at a state level and something is at a local level, there are always certain things which fall between the two, and it is a good analytical tool to understand water governance and power relations. And last is post-structuralist political ecology, which acknowledges that knowledge is power, and with knowledge you can extend your power relations, and then there are inherent power relations within our communications of drought, within our understanding of drought, and that social actors are producers and reproducers of narratives and sub-narratives. And I think the portrayal of discourse is very important to policymakers to sort out the intricacies of environmental issues, because it is only through the interpretation of texts or talks that we can recommend or recognize expected solutions for environmental problems. So my first finding was to identify the different social actors that were influencing the discourse on drought, and identified 13 different families of social actors. And there were 3 families which had a lot more frequency in the newspapers as compared to others, and those were agricultural community, municipal corporations, and state government. While municipal corporations and state governments enjoy certain social and economic resources which allow them to be represented by the newspapers a lot more often than others, it was also the recognition that the sources that come from them are relevant and official. So newspapers are more likely to focus on sources which they deem are more relevant and more official. So a statement from a minister or a statement from the state government is considered a lot more relevant than a statement from a farmer. So it was found that in the newspapers, indigenous or local knowledge was not as represented as official knowledge. And when it comes to agriculture community, although it observed the highest representation in the newspapers, it was found that most of their representation was passive. And what I mean by passive is that farmers were often endowed with passivity and they were withdrawn from a participating role in the narrative. To elaborate, they were often seen as objects. So they were often seen as beneficiaries of a new incentive, and rather than taking on a participating role where they tell you that this is exactly what we want to tackle droughts, they were often seen as those who would be benefited from an opportunity. They never got a voice to explain what their concerns were and what the possible solutions that they could offer. So in that instance, newspapers impersonalize farmers, and they only look at them as someone who's a commodity or an object who would only be able to benefit from something like drought management policies. And whereas, of course, municipal corporations and state governments were seen as official sources which invoke legitimacy and credibility. There were, in addition to these 3 relevant, most frequent social actors, there were other findings as well. For instance, NGOs, local panchayats, social activists, experts, they did not observe a lot of representation in the newspapers. And I think that points out to the fact that most of these voices were the ones that did not support the drought policies that were brought in by the state government and municipal corporations. So it makes you realize that dissent is often not covered in newspapers, and that the media discourse often focuses on popular sources rather than focusing on sources who are working on local grounds and who have more to say and have a better understanding of what a drought entails and how it affects different individuals. And then there's another aspect to this finding, which is that there are some shadow actors. And what I mean by shadow actors are those who prohibit implementation of successful water policies. In the case of Maharashtra, the social actors were water tanker associations who often cause illegal leakages into the leakages and are responsible to some extent for drought exacerbation, but they were never mentioned in the newspapers, even though there were some instances where they were connected with the municipal corporations, and even though they might have a bigger role in how we focus on drought management in the state, there were no references to shadow actors. There were no statements from them. So as I move to the next slide, I'll be looking at the different narratives and sub-narratives which fed into this drought discourse. So there were 2 main narratives that were found. One was water shortage narrative, and the other one was inadequate water management narrative. And then there were 3 sub-narratives that fed into each of them. The idea of water shortage narrative was that there is an inherent shortage of water in the state, and which is why we need to come up with better policies to make sure that we have a better supply of water in the state, whereas water management narrative said that I think we have enough water in the state. The problem is that we're not managing the water that we have. And the sub-narratives mostly blame different actors and different aspects. For instance, climate change, the narrative of climate change blamed climatology, seawater temperatures, and whereas the sub-narrative of exponential population growth blamed peripheral communities and migrants who are already disadvantaged and are very powerless. And when it comes to inadequate water management narrative, there were narratives such as exploitation of groundwater resources or unsustainable water use by agriculture users. And in both instances, they were blaming actors such as farmers or those who live, who are peripheral communities who exploit groundwater. And in that instance as well, they were blaming actors who could not do much, who were mostly powerless, and they did not have another source to ensure that they could get access to water. And so as you see, in each instance, there were different actors who were getting blamed and different aspects who were getting blamed. And in doing so, they were making sure that they were externalizing the blame and preventing themselves from being at the center of the issue. So anytime they blame climatology or El Nino as the only factor which causes droughts, it presents the idea that the policies are not to be blamed. The communities, whether those who are living around who are exploiting groundwater resources, are not to be blamed. And similarly, there were very distinct actors who were promoting these different aspects. And as these narratives were brought out, we also realized that these narratives then further push different agendas and push different solutions to drought management. And as I move to the next slide, you will see that. So most of the supply-based solutions, which were around construction of new reservoirs and river linking projects, had different discourse collisions. For instance, state governments, national government, and municipal corporations were pushing forward to make sure that we have more supply in the state, whereas everything on the demand-based solution was focusing on closure of registration of illegal wells or charging water tariffs or regulation of water supply for irrigation. So it brings out the idea that there is a very distinct connection between sub-narratives and the solutions we support and their supporters. So in order to make sure that it is very essential to incorporate media discourse and to realize the significance of influential interests. And it is also very important to realize that we can't simply build and force discourse, but rather there is a very strong relationship between social actors and the discourse. And discourses often give stages whereupon interests associate. And this is the reason why different solutions are sanctioned by different discourse collisions. And of course, though there can be an overlap, the purpose of a discourse collision is to guarantee the adoption of an endorsed solution. So every time you read the newspaper, look at the media, there are certain discourse collisions, there are certain actors who are pushing forward for that one solution. And in order to make sure that other people fall in with them, they use the media more recurrently as compared to those who are powerless. And as I conclude, I would say that this research is only a starting point to comprehend discursive practices which are associated with droughts, and to look at how these discourses impact the policies that are proposed and implemented by policymakers. Thank you.
Thank you very much, Hanor Kaur. That was very fascinating, especially for someone like me from the physical sciences, to see all the links that you make and that we do not often are aware of, I think, which are very important. Professor Yuei-An, would you like to take over for closing the session? I don't know if there are any questions.
Hello, Tom, and all speakers. Thank you all for participating in this meeting. Unfortunately, I was not able to join because of a technical problem, as I would say that I was at home and I came to the office for this meeting as an organizer. So thank you all for your join this session. I did not hear all the speeches, but I think let me share what is happening in Taiwan now. I think in the context of climate change, we suffer different kind of nature impacts, such as drought, that is of a main concern of this topic. And it's one of the issues that many countries encounter. So it's very crucial to study this area. And I use Vietnam as an example in the I think for this session. But let me assure you what is happening in Taiwan now. Taiwan used to have more water instead of less water, but now because of shortage, actually last year, no typhoon hit Taiwan. This is the first time in history no single typhoon that hit Taiwan in a year, and the typhoon is or cyclone or hurricane. Primarily is the source of water of the country, and without typhoon last year, Taiwan is suffering shortage of water now. So essentially, kind of a drought problem we are encountering. So this is an interesting thing that is happening here now, and this I would say that this is also related to possibly climate change. The tracks of a typhoon has been influenced, and as a result of change in the typhoon tracks, right now the typhoon seems there's a trend for the typhoon to move to the north Pacific, West Pacific, instead of taking the track as usual. If the typhoon move as the usual tracks like before, generally 2 or 3 typhoons will hit Taiwan. But last year, no typhoon did so. So I think in the context of climate change, many impacts associated with the climate change, the scientists have to pay attention to that and do our best to investigate how to understand the natural disasters, drought, typhoons, whatever, and figure out the measure how to mitigate the society to this type of impact. I thank you all, and I think this is not directly related to the presentations. So let's hear. Let's see if any questions from the audience, and before closing the session. Any questions for the speakers for the last as well as the previous?
I'm watching the chats, but I don't see any questions. So yeah.
Okay.
I want to thank you also. Thank you, Yuei-An. I think it's fabulous to have this kind of conferences, even though it's online. But we can have people meet from Latin America, where it's early in the morning, to you, where it's very, very late at night already.
It's very late for me now. Yeah.
So yeah, no, really great to hear what's going on in Taiwan also, and really missing the conferences, and hoping that soon we can all meet again in person. Thank you.
Thank you. So if there are no questions, so we are going to close the session. Okay. Bye-bye to you.